In this module, we will look at a very important class of machines called permanent magnet AC machines. And in the past, these machines were used at fairly, they were limited to a few kilowatt, let's say, in rating. But now they are being used in fairly large sizes, such as for wind generation up to 5 to 10 megawatt level. So, we certainly should know how these permanent magnet AC machines operate, and then later on how to control them. So we will begin with a simple description of what they look like, how they operate, and how the torque is produced in these machines. And also we will look at, in a very simple way, how we can supply the currents into these machines to control them. So let's look at the block diagram here. They are always, most of the time anyway, operate in a closed loop fashion here, as shown by this block diagram, where we have power coming from the utility, and then we have this power processing unit made up of power electronics that, under the direction of this controller, is supplying these currents into this sinusoidal PMAC motor that we will see in a minute, and driving this load. But we also need to sense the position of this rotor, as we'll see the need for that. And that sensed position at any instant of time goes into the controller in order for the power processing unit to determine what currents ought to be supplied. So let's look at the structure of this type of machines. On the stator, we have a sinusoidally distributed three-phase windings, as we have seen in previous modules in a general AC machine. But on the rotor, we have permanent magnets. So here they are represented as north and south poles, just a two-pole machine, but it could be any number of pole pairs. But it sort of makes it simpler just to talk about just a single pole pair, as shown here, and how these north and south pole are, these magnets are attached to this rotor are not described except to show that we have a north pole on one side and the south pole on the other side. And we will measure the rotor position, theta sub m, as shown here, with respect to phase A axis. So as the rotor rotates, this theta sub m would change. And so these magnets are also arranged such that they produce a sinusoidal flux density distribution in their gap. So we can represent that flux density distribution by a space vector, B sub r, as shown over here, the space vector. And of course, its amplitude remain constant, but its orientation, this theta sub m, would change as this rotor rotates. So the next thing is, how do we get some torque out of this generator or this machine, whether in a motoring mode or in a generating mode? So what we see here is that, first of all, the flux density distribution produced by the permanent magnets in the rotor is represented by this equation here, and on this diagram by this space vector over here. So what we really would like to do, and we'll show that in this slide as well as in the next, that in order to get the maximum torque per ampere, we should place the stator current space vector 90 degrees ahead of the rotor flux density space vector, 90 degrees ahead, in the direction of rotation. So this is being described in the motoring mode. So if you want to make this into a motor, we would like the stator current space vector to be placed 90 degrees ahead of B sub r space vector in the direction of rotation. So in this case, it's in the counterclockwise direction, like this here. So by placing this stator current space vector 90 degrees ahead, as we saw early on in a previous module, that there's a physical interpretation associated with this stator current space vector. That is, it is representing a hypothetical winding which has an orientation such that its MMF is along the stator current space vector, and it is sinusoidally distributed as shown in this diagram over here. So if I sub s is over here, then this hypothetical winding has the magnetic axis along the same axis as I sub s, and it has this current IS hat flowing through each of the conductors, and you can see that the maximum conductor density then is where the flux density distribution is maximum. That is where the stator, the rotor flux density space vector is oriented. So the maximum current density, conductor density, not current density, but the maximum conductor density of the stator is at the same location where the maximum flux density is produced by the rotor. And this we can prove would result in maximum torque per amp. So first of all, we could have taken any general orientation of I sub s, but we can just physically see that if it was not in the orientation as we saw earlier, some conductors would be producing a torque in the opposite direction and compared to the others, and that will not be the optimum condition. So 90 degrees is the optimum condition, and we can calculate the torque that will be produced, although we may not be using it, but it's helpful to know. And that we could do by, first of all, to make our life easier, say that this B sub r space vector is horizontally located like this. In that case, I sub space vector is over here, and we can see this hypothetical winding orientation, and we can take some angle zeta, and in this differential angle d zeta here, we have this many differential number of conductors. The current is IS hat. The length of this this machine, let's say, is L. So that's the conductor length. And the flux density at zeta in terms of its maximum BR hat is this here. So using this fundamental principle that the force produced is BLI, we can calculate the torque, or differential torque, in this differential number of turns by multiplying this force by the radius r over here of the machine. And then to find the total torque, we integrate from zeta of minus 90 degrees to plus 90 degrees. And just by symmetry, we just need to do that and multiply by this factor of 2, and we get this expression over here. So what we see here is that this torque that we have is proportional to this IS hat, the maximum value of the stator current space vector, and it's related to the machine quantities, which are not going to change: the number of turns, the radius, the length, the peak of the magnetic, the flux density that is produced by the magnets. So what you see here in brackets, that's really a constant K sub t, which we'll call a torque constant, and its value is over here. And the electromagnetic torque produced is equal to this torque constant times Is hat here. So just like in DC machines, permanent magnet DC machines, we can control the torque by controlling the armature current. Similarly, in these machines, so-called brushless DC machines, because there are no brushes, we can control the torque by controlling Is hat. So that's why this name brushless DC. So that's the similarity that is shown in this slide, where we have in a DC machine magnets on the stator, and on the rotor we have an armature winding, and which produces this armature flux phi sub a, which is at 90 degrees to the stator flux, which is stationary because the magnets are stationary, and we get the torque controlled by the armature current here. Whereas in this brushless DC machine or Pmac machine, we see that we have magnets on the rotor, and this rotor is rotating. Therefore, this B sub r that we get is rotating but intentionally we put the stator current space vector always 90 degrees ahead of the flux density space vector Br in the direction of rotation. If you want to make this into a motor, and it will be 90 degrees behind if this were to be a generator, and you can see that there's a great deal of similarity here. The only thing is that we need to make sure that we have appropriate currents in phases A, B, and C to put the stator current space vector 90 degrees ahead of B sub r space vector here. So we know this electromechanical equation here, that the acceleration is dependent upon the difference between the electromagnetic torque that is generated and the opposing load torque, and divided by the equivalent inertia of the system, assuming damping to be negligible here. So that's the acceleration, and which is d omega dt, and therefore we can calculate what omega would be, this initial speed plus the acceleration over time. And similarly, knowing the speed and knowing the initial position, we can calculate what the position of the system would be at any instant of time t, which is the initial position plus the integration of the speed over time. So if we wish to exert or derive certain amount of torque, then we need to know the motor torque constant Kt, and also we need to supply appropriate currents in these three phases at any instant of time, such that this Is vector is 90 degrees ahead of the B sub r vector, and it has the right amplitude. So to find the amplitude, knowing the desired torque that we need to produce, and knowing this motor torque constant, which may be in the motor data sheet, we can calculate what the amplitude of this stator current space vector would be, and knowing the position of the rotor that we have to sense, and knowing that the stator current space vector should be 90 degrees ahead, we know what the orientation of this current space vector would be. So knowing these two quantities over here, we can at any instant of time calculate what this stator current space vector is. And as we saw in the earlier module, since these three currents add up to 0 due to Kirchhoff's current law, we can individually calculate what these three phase currents ought to be supplied to this Pmac machine. So this is sort of illustrated by means of a simple example where K sub t is given as 0.5 Newton meters per amp, And in this case, we need to produce a holding torque. That means it's given that we need to hold the rotor for whatever reason at 45 degrees with respect to phase A axis. So given that, we can calculate what the currents in phases A, B, and C need to be. And they turn out to be as shown in this example of these values over here. And these are DC currents. So it's a PMAC machine, but so you can also see the power of space vectors, that they work with DC quantities, because the sinusoidal distribution is coming from the fact that these windings are sinusoidally distributed. So in each of these three windings, the current that are being supplied are DC, because we want to hold the rotor at a constant angle of 45 degrees. It's not moving, right? So the currents are also current also should not be changing with time, so they are DC. But we are able to apply this space vector concept very nicely here. So that shows the power of space vectors. So here it brings us to the summary of this module, which shows that we can that we have looked at a very important class of machines, PMAC machines, and how they operate, how we can calculate a torque in them, how they are similar to brush type DC machines, and we can also calculate what the currents have to be and where they have to, and well, let's just put it, what these currents have to be in each of the three phases to supply the torque in a way that torque per amp is maximum.